So I've just told you the difference between mean field theory and dynamical mean field theory. And told you that in order to do this, what we need is the solution to what's called the impurity problem. And that gets called an impurity solver. In order to do this update process, where we update the bath, we solve the impurity problem, we update the bath, we need an impurity solver. And it turns out, most of the computational effort is inside that impurity solver. The process of updating the bath is just a very quick redefinition of things before you fire it back into the impurity solver. So realistically, any solution method is totally fine. However, exact diagonalization is very quickly not feasible as you increase the complexity of the impurity. And by that, I mean the number of degrees of freedom of the bath, essentially. So depending on what you're trying to do, you can extend this to multiple lattice or multiple orbitals. But because of the complexity, that you're talking about some high-order, high-dimensional problem, is that typically people move on to looking at Monte Carlo methods. So the one that I've employed the most is a continuous time auxiliary field Monte Carlo. And so what that basically means is that an auxiliary field method, and we've already talked about this, is that by doing a Hubbard-Stratonovic transformation, we have now added in some auxiliary objects that have to be integrated over. Now, the details of this method allow for some decoupling. So we have the problematic term on the left-hand side, which was this NN. And on the right-hand side, it looks like some particular form, which has some S, which looks like a plus or minus. And now the N terms are separated from each other. Okay? So those S values that can be pluses and minuses now look like some weird spin, some auxiliary spin object that did not exist explicitly on the left-hand side. So at least within this method, you can do some work and you can try and write down a partition function. And that gives you the framework for trying to evaluate some Monte Carlo weight for a particular update. Now, Lichtenstein last week went through this actually in explicit detail. I don't know how many of you recall. He wrote out explicitly the Metropolis algorithm that he was using. And he wrote out essentially the same partition function. And he even showed you for different lines exactly how you consider the interactions between these spins to write down the partition functions. Okay? So if you go and look at his talks that presumably will be posted, all of that will be there explicitly. The thing I want to point out is, from your coursework, how many of you have done a 1D or 2D icing model as an exercise for a Monte Carlo problem? Okay. So typically, a 2D icing model is a pretty standard Monte Carlo problem. When it comes to the updates that are required to do this process, the summations that are required in here are essentially all values of spins at all values of times within this imaginary time confinement between 0 and beta. So it actually looks a lot like a 1D icing chain, okay, with a bunch of spins up and down, except they're not on lattice sites. They could be at any particular time. Okay? So the updates that you require look like maybe global spin flips, individual spin flips, choosing to change them to different times, adding in a new spin, removing a spin. So the updates are actually quite simple, but the probability weightings have a little bit more work, and Lichtenstein talked about how they get represented as a determinant. Okay? He even talked about something called Hirsch-Phi, which is where you discretize this time scale and you only allow spins to exist on those sites. The early versions of dynamical mean field theory used what was referred to as a Hirsch-Phi solver. Continuous time solvers simply take that limit of delta t going to 0, where you allow any times. Okay? It's computationally a little bit more expensive, but it avoids what's referred to as a Trotter error, or Trotter decomposition error. Decouplings are really important. I didn't talk about it when I was talking about the extended Hubbard model. But when you have the extended V term, the decoupling is a little bit more complicated. I'm not going to go through this in detail, but the whole point is that decoupling schemes do exist. Okay? So I made a big fuss about this in the first lecture, and I think it's a really important point, is that for most of these Monte Carlo procedures to be tractable, you realistically have to have some sort of decoupling scheme that removes that complication and allows you to explicitly write down a partition function. OK. So DMFT is the remapping of this lattice problem to an impurity and a bath. And we're going to repeatedly update that bath. And we know already from discussion that that is not necessarily a good solution for certain things like phase transitions, where finite size effects become strong. The reason is that the self-energy that should be a function of k and omega, when you have a DMFT self-energy, it has no k dependence. It's just a frequency-dependent object. So you can imagine that right away, that's a pretty coarse approximation, right? So one way to alleviate that is dynamical cluster approximation, which is a momentum space cluster type method, where it forces that there is, in fact, a momentum dependence, but that momentum dependence is coarse-grained in certain regions. So for example, everything, the self-energy in this yellow region is the same everywhere, and it's the same everywhere in the blue region. OK? But it's a different value. And similarly, as you increase the system size, you add more patches, and you allow a finer coarse graining to your self-energy. And this effectively pushes you towards solving the thermodynamic limit problem. OK? Great. The other method I've talked a lot about is diagrammatic Monte Carlo. Essentially, what people typically have done is evaluate something called a skeleton series for either a self-energy or more likely a Luttinger-Ward functional. And this is typically done actually in imaginary time. And one of the reasons for that is that, at least for certain problems, in imaginary time, these objects become real. And that helps with something called a phase problem, which is where you add two complex numbers. And when you average them, they become very close to 0. OK? This is an interesting technique, as I mentioned before, because it's very easily in the thermodynamic limit by just not restricting the values of k that you're going to use. By not coarse graining k, you allow all possible momenta, and you're essentially solving the problem for an infinite system. In this Monte Carlo, they actually have to have some method to change diagram topologies. That means they have to be able to take two Green's function lines and pinch them together and say, I'm going to add a new vertex or a new interaction line between two Green's functions. And by adding those lines in and removing them, they can change topologies. So that's one thing they have to do. I talked about that quite a bit yesterday when I was talking about this algorithmic Matsuberry integration. But the other thing they have to do is actually modify internal variables. So what you'll see if you look up the literature for diagrammatic Monte Carlo is you'll see that they do this via something called a worm algorithm. And this helps simplify the updates. This is something that was kind of mentioned by Lichtenstein the other day. He talked about two things in Monte Carlo, and one of them was something called detail balance. And so by minimizing the size of the updates in a Monte Carlo process, you maximize the number of measurements or the number of updates you can get through in a certain amount of time. So what diagrammatic Monte Carlo does is it actually goes between momentum conserving diagrams to non-physical momentum non-conserving, momentum violating diagrams. And it does so by inserting a worm, an extra line or an extra object in a diagram that carries momentum and energy. And it wanders through the system until it either meets another worm or it forms ultimately a closed path, OK? Which is by forming a closed path, it's essentially met another worm. So if you take any Feynman diagram and you find any closed loop within it, and you change the momentum on every point in that loop, you have always maintained conservation of momentum. OK? So that's the idea here. But they break that process of finding a closed loop into incremental steps. And that helps with something called detailed balance. So if you're not familiar with Monte Carlo, this is just trying to give you an overview.
Yes.
Yep.
You maybe comment between use of this algorithm where you artificially, say, violate the conservation laws, and just real space Monte Carlo, diagrammatic Monte Carlo, where you don't have conservation laws. What's your current preference?
everything I've ever done has been in momentum space and directly having to worry about conservation laws. However, it does appear that there are new techniques that operate in real space where that appears to be a pretty major savings, at least when you're still dealing with this issue. And I think the key is that by inserting all of these non-physical diagrams, when you have a non-physical diagram, you can't make a measurement in your Monte Carlo. So it can actually be, if you have a system that struggles with finding another physical diagram, that you've wasted a huge amount of time, like 60, 80%, sampling non-physical diagrams. You're not finding a physical diagram again. So there's certain cases where that seems to come up. I think if that's not a struggle, I don't see that there's an advantage of the real space problem. But it seems like when it is a struggle at very low temperatures, that somehow the real space problem just happily is ignorant of momentum conservation. And I don't understand those details. It's a really excellent point. Right. And I mentioned yesterday that moving forward, I'd like to try and eliminate a lot of that overhead in Diagrammatic Monte Carlo using this semi-analytic tool in between. And we'll see whether or not in the next couple of years if that has some value. There's also applications of this stuff to other techniques, for example, dual fermions. So I wanted to take an opportunity to talk about the method of dual fermions because it's something I've spent a lot of time working on recently. To the best of my knowledge, it was basically introduced by Alexei. And the key is really a Hubbard-Srutanovich decoupling. And this was, again, gone through by Sasha Lichtenstein, quite detailed in the fact that the decoupling is a little bit abnormal because it's not just decoupling of the U term, but in fact also decoupling of the kinetic energy piece, where you have these two fermionic operators. And when you decouple those things, you're now introducing some new auxiliary object, which they call these F or dual fermions, which actually I guess are more like Grassmann variables or something like this. And the idea in that method is to actually take dynamical mean field theory as your starting point solution. So the idea is you would actually solve your single site impurity problem. And then you're going to do an expansion around that. Rather than physically make your impurity bigger, you're going to do an expansion around that problem. Okay? Now, when you do that, you come up with something that looks very simple and very solvable. But then you have some extra weird piece that just has some interaction V. And that interaction V is an absolutely horrendous object. Okay? That interaction V includes high-order vertex objects at the 2-particle vertex, so 4-leg vertex objects, 6-leg vertex objects, et cetera, et cetera. So it's described by this gamma to the 2n, okay, from n equals 2 and higher. And it's an infinite sum of vertex objects. All right? So I want to try and give an idea of what is it that means. So it's Lichtenstein again commented that in application of this procedure, which up to this stage is exact in that you haven't made any approximation, this is not tractable because you, at least at this stage, cannot measure those vertex functions for all of these high-order vertices within a dynamical mean field tool set. You run into problems of storage. I talked about this where you have too many variables attached to these objects, and the size of those objects becomes computationally untractable. Okay? So what was the role of duality in this, other than the fact we've got these new fermionic operators? Just as we saw earlier, the dual transform basically takes the effective interaction into the dual space. So we had a j over t going to a t over j. We now have an interaction u. Okay? So what that means is that as u gets very large, rather than being a directly large term in the Hamiltonian, in this weird dual space, it's actually somewhat a small object. And so Lichtenstein also talked about this sort of picture. So this is a t versus u phase diagram. And I'm just sort of saying regions which are good and regions which are bad. It's an interesting procedure because when you're weakly coupled or when you're at high temperature, you've done an expansion around dynamical mean field theory. And at high temperature, dynamical mean field theory gives you the correct answer. Because at high temperature, your self-energies are not overly momentum dependent. They're quite unstructured. So it gives a very good representation of the self-energy. So at high temperature and weak coupling, DMFT is typically correct. And so you have a good starting point for dual fermions. Dual fermions won't produce any corrections. So you have a large region here, which is correct. But because of this inversion, you now also have the strong coupling region is correct. So it creates this interesting dichotomy where you're not just having a weak coupling expansion, but you have a weak coupling expansion on top of a strong coupling expansion that somehow merge in the middle. So what does this look like pictorially? This is where I'm trying to diverge from the math. Pictorially, again, we said we had a DMFT problem, which was we took our lattice and replaced it with a single site sitting in a bath. Okay, that's what's shown here on the left. In dual fermions, the idea is that every lattice site is now an impurity. But the impurities, we decoupled the C dagger terms. The impurities are not allowed to jump from one lattice site to another. They're allowed to jump from a lattice site into, I've called it the red region, okay, in general. So remember when I wrote down that dual lattice, and I showed that for a square lattice, the dual lattice lives sort of in between. In this case, for an infinite system, it's literally the case that the dual fermions are allowed to exist every point in space that's not on a regular lattice site. Okay? So you're allowed to essentially hop as an electron from being an electron on a lattice site to being a dual fermion in this dual space. And then you can just propagate through the system anywhere through this red region, and sometime later hop back onto a different lattice site. Okay? So you've created highly non-local interactions. And every time you do that, when you hop on or off, you pay a cost associated with a vertex function, okay, of the original lattice problem, or sorry, the original impurity problem. Okay? And this vertex is some truncation of these vertices. So typically, we truncate it only at the n equals 2 case. So we only include the 4-point vertex, which we symbolize by that gamma function. I talked a lot about that gamma function. In truth, there's a subtle difference, which Alexei pointed out the other day. I didn't go through the details of talking about Parquet equations, the difference between the fully irreducible vertex and the full vertex. So for now, I'm just not going to worry about those. You can go and look up the what I marked as the best paper ever by Georg Rohringer, which explicitly outlines all of those subtle details. Okay. So when we've done this, it's really cool because long-range correlations have somehow become very local for the dual fermions. Okay? And they're dependent only on properties of the impurity. But the details of doing that include all higher-order Green's functions of the impurity problem. So the procedure is as follows. We solve the impurity problem. We get a Green's function, or a self-energy, that has no momentum dependence at all. Once we converge that, we actually solve the impurity at some higher order. That means we directly try and measure this 2-particle Green's function that has 2 fermionic frequencies and a bosonic frequency. But there are no momentum labels. So I talked about the problem of scaling of a 6-dimensional object that had, in general, you would have a 4-point Green's function that had 2 frequencies, 2 fermionic frequencies, and a bosonic frequency. But matched with it, it would have a k prime, and a q. And I commented that in order to store this object, you run into a lot of problems on a proper system that has momentum. But because we're doing DMFT, there is explicitly no momentum dependence. So this object for DMFT is actually tractable because it's not a 6-dimensional looking object. It's more like a 3-dimensional object. So that's really important, the fact that this becomes a tractable problem. So we can actually solve for higher order chi's. Susceptibilities, vertex functions, all of that stuff comes through the beta-Salpeter equations. We run this through dual fermions, which in our case is a published code referred to as open dual fermion. So it just takes that vertex, it takes your Green's functions and your self-energy. And it, I would say, via magic. It takes a Green's function that has no momentum dependence, and it produces a Green's function that has momentum dependence. It reinstates that momentum dependence. And it takes that momentum dependence from knowledge that's somehow hidden inside that two-particle vertex object. Okay? All of the details of the single particle physics are somehow hidden in that vertex object, despite the fact that the vertex object itself didn't actually have any momentum dependence. Okay? Conceptually, in order to get the correct answer, we would need higher order vertices. And all of those higher order vertices also don't have momentum dependencies. OK. So this dual fermion method produces those momentum dependencies. I think it's really important, because this is a school, to mention. Yesterday, Guy went through a really great, open discussion about what tools do you guys use, what is available to save you time, that sort of thing. How should you prototype codes in Python rather than straight away write them in C++? Now, this is a little bit of an advertisement. For a long time, there have been Monte Carlo libraries that have existed. A number of years ago, one of the more popular ones, which was referred to as ALPS, Algorithms and Libraries for Physics Simulations, has been taken and somewhat rewritten with the intention, with an actual staff programmer named ALPSCore, with the actual intention of producing an object that people can really use. Okay? Not just a tool for the students or the people who developed it that happens to be online, but a tool which includes full and clear documentation and examples, et cetera, et cetera. Okay? So I encourage you, if it is the case that you have to write some sort of Monte Carlo code for any purpose, okay? And you have to do it not in Python, okay? Not in a prototyping language, but for a high performance type purpose, I encourage you to look up ALPSCore, or there's a competing free version, not really competing, they're friends, Trix, which are released with the intention of containing all of the basic elements you need to do Monte Carlo. So the basic packages included in ALPSCore include parameter handling, okay? Which sounds like a trivial thing, but parameter handling in precisely the way computational physicists want parameter handling to operate, okay? And hopefully making some improvements there. Parameter handling in a way which helps you as a group, if you have multiple people working on the same code, to not make mistakes. For example, the inability to define a parameter without a description of what that parameter controls. No ability to hide a parameter somewhere in your code that is somehow unspoken and hard-coded to be a 4 or some such nonsense, which does occur. Okay? The ability to read and write to HDF5 files. How many of you have used HDF5 file formats in high-performance computing? Yeah. So surprisingly few. If you have some situation where you need to write routinely hundreds of megabytes to file systems or gigabytes to file systems, writing them as quickly as possible if you've got a highly parallelized problem is important. HDF5 is, at least at one point, was the leader in trying to do that. I don't know if that's still true, but it at least provides some tool to take all of the data for a simulation and put it in one file called an HDF5 file that knows about all the parameters of the simulation, all the results of the simulation, all the uncertainties, et cetera.
Yeah, so there are a lot of new things that have similar functionality. So the web programmers have recently discovered the NoSQL databases.
Yeah.
But HDF5 is actually the thing that you should use.
Yeah, I think it still is. I think it could change, but I think right now HDF5 is the thing. For many users, you're not at the point where this is a bottleneck, but there are situations where your file writing might become a bottleneck. Okay? Tools to manipulate Green's functions. That's not overly interesting. It's mostly offloaded on Eigen3, which is just tools to manipulate vectors and matrices, et cetera. Okay? However, the key things are all of the statistical analysis. So accumulators, binning estimates, log binning, et cetera. Things that have been solved for years and years. And if you're going to sit down and rewrite them, you really are reinventing the wheel. Okay? trivializing the process to go from a serial code to an MPI code, okay? Forcing the structure of your code to essentially be such that within just 2 lines you have a trivially parallelized MPI code. Most importantly, it includes explicit tutorials. Tutorials which include codes for example, 2D icing model simulations. So if you ever have to write one for a course, you can just go and take it from here and run it, and at least make sure that what you have is correct results. But more importantly, you could just take one of those existing simulations that includes the basic features of a Monte Carlo code, which are, you have a configuration, you propose an update, you decide to accept or reject it, you update your configuration, and you continue. Or you make measurements, and then you continue. You can take any of these Monte Carlo codes and pull a few, maybe 100 lines of the code out and put your own simulation in. Okay? So what it means is that the 300 or 400 line code, you only have to write 50 or 60 of the lines in order to make something work. Okay? Similarly, I mentioned that if you need to do maximum entropy inversion, we have codes that do that sort of stuff. So if you ever obtain data in Matsubara axis, you can convert those things over. I'm not going to focus on this so much. OK, so I'm actually pushing into what is the last segment of my lectures. And the goal was to try and give some example problems. And so I'm going to focus on 2 things. Things I've worked on. One is so I went through quite an effort talking about obtaining consensus on single particle properties. The idea is that we also have the tool set to construct these 2 particle objects. So these might be susceptibilities and vertex functions. And that those are really very relevant to experimental work. So I'm going to use those 2 particle objects to try and tackle a couple of problems that have existed in the literature. And one of them is understanding the pseudogap physics that occurs in the Hubbard model. And maybe that has some relation to the pseudogap physics that occurs in the cuprates. And then also some suggestions on superconductivity and how we can search for optimal TCs within a particular model. Okay? So these are very specific applications of some of the things I've talked about. So I want to start with a thought experiment. The other day, Sascha Lichtenstein was showing all of these DMFT plots. And there were a couple of students who showed confusion as to how he was drawing conclusions about physics that was in the band structure. And I think I can only say that it's from years and years of experience that he's capable of doing that, and knowledge of those systems. And to try and illustrate that, we have a thought experiment. So the thought experiment goes like this. I don't know, you're the theorist in your institute, and some experimentalist from down the hall measures the density of states of some material. He doesn't even know what it is. Maybe it's an undergrad. I don't know. They come to you, they say, I've measured the density of states of material X, and it's shown on the left here. And they say, what does it mean? Okay? And you look at it, and with a realistic viewpoint, you see, OK, well, there's some states over here, and there's some states over here, and there's kind of a gap, and there's some little peaks here. So the gap probably has some amplitude. There's no scale on the axis, because it's not real data. I drew it by hand. So what do you guys think that that means? I mean, all day I've been talking about insulating physics, right? So what does this actually tell us is completely dependent upon your bias as to how you're going to interpret this. If you work on strong coupling models, you would look at this and you say, oh, that's an insulator. However, if you work on cuprates a lot, you'd see these little peaks up here, and you'd say, I bet that's a superconductor. Now, isn't that a weird thing? How I could have how close is the physics of an insulator and the physics of a superconductor? Presumably not very close, right? I mean, there's some pretty fundamental differences in terms of how current flow. They're complete opposites, okay? But when you look at just the density of states, you have no idea what you're looking at, okay? You have no idea what has caused this. So there's other people who would say, OK, well, it could be some hybridization gap. There's some ordering, and there's some other particle that's come in, it's hybridized. And that's a just as valid explanation. And there are thousands of other explanations, things that can cause such dips in density of states. So this issue arises in experiment. It arises in numerical work. And the theme that I'm trying to present here is that this is a single particle quantity. Okay? The density of states. It's sometimes called the single particle density of states. It does not know about the physics of the phase. It does not know those things. It is not allowed to. It is the single particle property. Two particle properties, like susceptibilities, like vertex functions, those are things that get to know about phases. And unless someone shows you one of those, you can't really say much about what's causing the physics. Okay? So the conclusion you draw from this is that there is some number, maybe, which is a gap, and it's maybe like 5. Some number. So there's not a lot of physics in the number 5, I think. I don't know. It's just a number. So the same thing happens when we, so just to try and explain more about what's gone on here, recall that definition of a self-energy. We put a particle in the system, it propagates through, and then we pull it out sometime later. Or your drunken man winds up at home, or he winds up at a friend's house, but you don't know which bars he went to, right? You've actually lost information. You've lost or averaged out the information as to what were the most important interactions, as opposed to some interaction that's there but not important, not causing a phase. Okay? So inside the self-energy are all the details of the interactions, and the question about which interactions dominate is really hard to detangle. Because there's lots of different types of interactions. We can have particle-particle type interactions that might be associated with like even superconducting states. We can have particle-hole interactions that contribute to screening processes. We can have singlet formations. We can have triplet formations. We can have spin and charge excitations. Right. So understanding which interactions dominate a problem is really central to understanding the physics. And this is not just some theoretical problem. In the cuprates, this exists, and it's existed for, I don't know, 30 years, the problem of the pseudogap. So the pseudogap in the cuprates is as follows. When they look at the Fermi surface for a doped material, instead of finding a Fermi surface that they would expect for a tight binding dispersion, which might look something like this, okay? When they look just at this region, and they do this with angle resolved photoemission spectroscopy, they get something that looks like this. They find that there's an arc that they sometimes call a Fermi arc, where there are finite numbers of states shown by the colors. And they find in what they call the antinodal region that there is essentially no states there. So in this region, there's no states at the Fermi level, but over here there are. So it's like a somehow momentum selective insulator. Like over here, it's insulating. So electrons don't move in certain directions in k-space, right? They're not allowed. They only flow on diagonal directions. And they can actually go ahead and they can plot the amplitudes of those gaps, and they find that they're D-wave-like. They have a D-wave-like form factor. And then they can trace where in phase space they exist, and they live somewhere up above a superconducting dome. So there's a lot of controversy as to what is the origin of that phase, because as you come down in temperature, before you become superconducting, you go through this pseudogap phase, okay? At least for some region of doping. And so this is a big issue. And for years and years and years, people have said things like, the origin of the pseudogap is clearly superconducting preformed pairs. Clearly, because it lives so close to a superconducting phase. Or for example, its origin is the insulating phase because in its phase diagram, it leans up against the insulating phase. Or it kind of looks like an insulator, right? There's other models. You can write down many of them that give you pseudogaps from charge density wave order or spin density wave order or all kinds of things, on and on and on. Okay? And all of those produce densities of states. And all of those densities of states have little gaps. Okay? But it is completely impossible to distinguish which one is at play in a cuprate material. Okay? So we don't really have the ability to solve a cuprate problem, but we have the ability to try and address this within a Hubbard model, for example. Okay? The Hubbard model we already know it shows pseudogap phases, so we can try and extract some of that information, and our hope is that we can extract that from two-particle information. So this is not a new statement, the idea that we use two-particle information to get to know more about our system. STM and ARPES are single-particle probes. And experimentalists already know that they need to supplement these things with two-particle probes. Okay? And those two-particle probes look like optical conductivity, or Raman spectroscopy, or NMR, or neutron scattering. Experimentalists already know they need to do that. They need to look at those two-particle experiments, scattering type experiments, to understand what the physics is. Because if they get a peak in a neutron scattering experiment, it doesn't mean it's charge ordering. It means it's spin ordering. So the type of experiment is somehow specific to a certain susceptibility. And that susceptibility, it lives in a certain basis. And that gives you information about the physics. If that susceptibility is a magnetic susceptibility, or spin susceptibility, or susceptibility to formation of Cooper pairs, that helps you detangle what's the physics that's going on. Okay? So what we need to do is generate those analogous quantities. We have Green's functions and self-energies that live at the single particle level. We need to generate those susceptibilities. And I've already talked a great deal that we have at least some ability to do that for small systems, where the scaling of these additional k, k prime, and q degrees of freedom don't produce memory objects we cannot store. Okay? So long as the number of k points is small, we can actually, this is still a tractable problem. So again, why vertex functions? I showed explicitly before the inversion of a beta-Salpeter equation, which involved a vertex function. And when that inversion diverges, the denominator of that inversion diverges, it has to do with a phase transition. So vertex functions and susceptibilities contain the two-particle Green's function in some way. So they know how two particles are actually correlated to each other. So they know about phase transitions. They know how two particles are correlated. So they should contain at least all the information of phase transitions and long-range correlations. So this is just a stopping point where I should describe what is the high TC phase diagram that I'm talking about. So as a function of temperature, the half-filled phase diagram is an insulator, and it's surrounded by antiferromagnetic domes both on the electron-doped and the hole-doped sides. Okay? Both sides have a superconducting dome that's quite small in the temperature scale compared to the antiferromagnetic phase. But the physics that I want to go after right now is this weird pseudogap line that extends before we get into some sort of metallic phase. Okay? So the goal right now is to see how can we use two-particle properties to tell us the underlying physics in the system. And what are our tools that give us computational advantage in doing that? So I already kind of went through this. I'll go over it again. I'm going to skip basically the top half. So the goal is to use one of these dynamical mean field techniques called DCA, where we do a coarse graining in k-space. That says we pick a certain number of these k points that we want to reinstate, and we're going to compute its single particle properties. And once we've computed those, we can actually evaluate two-particle Green's functions that come through some particular sum of Wick's decomposition, which is what Guy talked about yesterday. Then we can write out the generalized susceptibilities through the Fourier transforms that I introduced the other day. And then we have an interesting tool set here, which were these Hedon equations. Okay? And what I want to particularly make reference to is the fact that we have Green's functions and self-energies, and then we have susceptibilities and vertex functions down here. But there are explicit formulas that get us from vertex functions back to self-energies. Okay? And that is precisely what we want to try and take advantage of. We want to say, I have this two-particle object. From this two-particle object, I can compute the single-particle object. Okay? And once I've done that, maybe I can have some intuition. And I'll give a description as to how to do that. So again, the problem I want to solve next is that we're going to put a particle in the system, and we've lost all this information. And we're going to use these two-particle operators, or these two-particle objects, to get that information back. So I think that's the right spot to stop. And we'll take a 5-minute break, and then I'll continue. Are there any questions about this? I haven't really shown you the key thing yet. So the goal right now is to understand from two-particle quantities what is causing pseudogap physics. So I need to explicitly define pseudogap physics. I went through the process of defining for you different metrics to describe metal and insulating behavior. And one of those metrics was called delta sigma, which was equal to the imaginary part of the self-energy at I omega 0 minus the imaginary part of the self-energy at I omega 1. Okay? So on the Matsubara axis, looking at the imaginary part of the self-energy. So we do a calculation using this dynamical cluster approximation. And we look at 2 points in momentum space. We look at a point which is referred to as antinodal, which occurs in a certain region of your Brillouin zone. And we look at a point which is nodal and occurs very close to a Fermi surface. Okay? And what you see right away is that we can use our definition of insulating type behavior as the sign ordering of these two pieces. And that says that here, the first frequency is above the second. It's trending towards 0. And that looks like a metallic solution for the point in the nodal direction, while the antinodal direction has the opposite sign. Okay? So here it looks insulating, while here it looks metallic. Okay? So for the context of what I'm going to present, this is what I'm referring to as pseudogap behavior. The fact that one point in momentum space wants to be insulating and another point wants to be metallic. Okay? If you kept going down in temperature, you would see more and more points become insulating until they're all insulating. So this says you go from a metal to a pseudogap, or a pseudogapped metal, to an insulating phase. So in order to understand what causes a pseudogap, we don't care about all the other frequencies. Okay? We only have to ask what causes this one feature. Right? So what causes the specific contribution to the self-energy that causes this frequency to be so much lower than that one? All right? I think this is a very concrete question. And we have the ability to answer that within small cluster DCA calculations. It's published in this paper here. So I like cartoons. I'm not sure if you're aware, but matplotlib has a XKCD plot. So if you've ever wondered where XKCD comes up with its really cutesy looking plots, it's a built-in function in matplotlib.
XKCD did it first.
Did they do it?
Yeah.
OK. Very good.
Someone added this functionality, and now it's like an official part of the
library. It's an official part of the library. So it's very easy to produce nice, cutesy looking things. I love it. So Guy kind of touched on this yesterday. He asked you how many parameters were required to describe a quantum mechanical system. And the answer was infinite. And that's only if you're in a number basis where you're really just going to pick up the number of points. There might be quantum mechanical systems where the number of points to describe the system is the number of eigenvalues or some such thing, right? Which might also be infinite. So I want to talk about what is the role of a basis representation, and what information do you gain about your system by your choice of basis. So we picked the simplest two things you can possibly write down, which is a square wave and a sine function. Okay? Now, a square wave is a very simple function. It has essentially two values, maybe three values, depending on how you want to describe it. Right? It has maybe on the x-axis some point where it jumps. Every point below is one value. Every point above is another value. So it probably needs about 3 numbers to describe it. It's a very simple function, but you probably know from your, I don't know if you took an electronics course or something, But basically, even from your quantum courses, you should have an understanding that in order to represent a square wave, if you decide to represent it for some reason in a Fourier basis, which you can go ahead and do, it's written as an infinite sum of some sine functions, okay? Or cosine functions or combinations. So, you know, one can do that, and there's reasons why you would do that. But the Fourier basis for a square wave is notoriously a bad basis to represent a square wave, right? But if you take a sine function, a sine of x function in the number basis is a complicated function in the sense that every point between 0 and 2 pi has a different value. And you would have to write all infinite numbers of points down, okay? So the number basis for a sine function is a very bad basis. But in the Fourier basis, it's actually described by just one number, okay? Now, the choice of basis does not impact the result. So you are free to change your basis how you see fit in any mathematical problem. And if that gives you some computational advantage, you go for it. So it doesn't change the result of the problem. But if you find a good basis, and I guess a compact basis, a basis that's represented the same function with fewer free variables, the finding of good basis actually tells you something about the problem itself, okay? Yeah, sorry, this was me playing with some, I don't know, maybe that's 5th order or 6th order terms, and it still doesn't quite look like a square wave. So this was in collaboration with Ole Gunnarsson, who's in Stuttgart, and Thomas Schäfer, and a bunch of Italians, and Georg Rohringer. And the idea was to take that equation out of that Hedon pentagon that relates a 2-particle object to a single particle self-energy. And the diagram looks like this little clamshell type diagram plus what looks almost exactly like a 2nd-order self-energy diagram, except that one of the vertices is not the bare vertex. It's the fully renormalized vertex function. Okay? And we know that when we perform all the internal summations over this gamma object, that we have different basis representations for that gamma object. But we know when we perform all those internal summations that the choice of basis cannot impact the self-energy, because the self-energy does not have a spin basis or a magnetic basis or a particle-particle basis. Okay? It is a single particle object. So what we can do is we can play a game. We can say, well, what if I don't sum all of the internal indices? What if I leave a couple of them? Okay? And what if I leave the bosonic ones? What if I just don't sum over the bosonic ones? And what this means is I can write a piece of this summation, and I'll sum over the fermionic degrees of freedom, but I'll leave the bosonic Q, and I'll leave the bosonic omega. And what that produces is the integrand that I would have to sum to get the full self-energy is now decomposed into a set of Q different values. And I've left it off, but also a set of different bosonic contributions. Okay? And this has been, they coined the phrase fluctuation diagnostics. And the idea is that by performing a partial summation over the internal indices, it actually provides us a window into the source of the interaction. Okay? Because we can do 2 things. We can examine the frequency, yes, both the frequency and the bosonic frequency, and the Q dependence. Okay? But more importantly, I don't know if someone's poster is going to die here. It gives us the ability to examine the basis dependence. And the reason for that is I have the same summation formula where I represent my vertex as a spin vertex or a charge vertex or a particle-particle vertex, and I have to get the same result for the self-energy. I do not have to get the same result for this partially summed object. Okay? Is that clear? So we go ahead and we do that. And there's some stuff on the left-hand side. It's just repetition of the equations on the previous slide. But on the right-hand side, is the graph that represents these results. And it's not a continuous plot. And the reason is it was done for only 8 points in momentum space. Okay? Because that's the level at which this is all tractable. And so we look specifically at the self-energy at that point where the system is becoming insulating. And we work out the contribution for different Q scattering vectors. Okay? And we ask, how does that change when we represent our vertex as a spin in red, blue is for charge, and green is particle-particle excitations, which have at least some connection to superconducting fluctuations. I'll talk about that in a bit. And what you see right away, what's the biggest part? Which color is it? Red. It's red. And it's this one. And it's pi pi, right? So there's two things that one takes away from this. First of all, if I represent it in terms of the blue charge or green particle-particle, is that it's very diffuse. Okay? All of the different Q vectors give about the same contribution. Okay? There's no special Q vector which is somehow important. But when we do it in terms of spin, we see that most of them are essentially 0 in comparison to the pi-pi spin fluctuation. And pi-pi spin fluctuations, if you look at that direction, those are associated with antiferromagnetic fluctuations. So that's an antiferromagnetic state. Okay? So it becomes pretty clear that the source of the self-energy, it's not that it can't be a charge excitation that causes this pseudogap. It's not that it can't be a particle-particle excitation that causes the pseudogap. It's that a spin excitation is a well-defined mode. Okay? So if I want to write down an effective theory, I need many parameters to describe a charge excitation, a complicated charge excitation, to give me the physics that gives me an insulating phase. Got it? But if I want to write down a spin model that gives me that insulating phase, I need one number. And I could just set the rest to 0. Okay? And that would be a good effective model. So this thing here looks like an actual mode. It looks like a spin mode. Okay? OK. So what we conclude from this, somehow I'm missing a slide that's supposed to come right after this and give those conclusions, but that's OK. What we conclude from this is that the physics we see that gives you a pseudogap is not superconducting fluctuations, and it's not charge ordering. It's antiferromagnetic fluctuations. Period. And there's no ambiguity here. It's completely concrete for the 8-site Hubbard model. Okay? 8-site DCA calculation of a Hubbard model. Who knows how that reacts or how that maps onto a cuprate problem, et cetera. Yeah.
So it's a Bayesian argument, basically, right? You said that this is the model with the fewest parameters, therefore it's most likely to be true. But as you said, it could actually be that it's charge excitations just...
No, it's not even that it could be. It's that it is equivalently and simultaneously. They are the same object, right? You could have some experiment finding really complicated charge excitation and some other experiment finding spin excitation. And they could, in fact, be the exact same underlying physics, giving the same result of a pseudogap, because it's just looking at a different basis object. Okay? So it's a little bit more than that. Like it's really deep stuff. Okay, so this is either my last or our second to last example. And I spent a lot of time in my PhD working on high TC cuprates. As you can see, there's a lot of cuprate-related content. I think it's really fun to go back to the 1960s and look at what was coined as Matthias's rules, which were formulated at some point as empirical observations for what provides a good superconductor. Okay? So the idea is saying, we're going to go look for higher temperature superconductors. How are we going to do that? Let's write down some rules that seem to apply. And they said high symmetry is good, and they said cubic symmetry is best. Cool. They said high density of electronic states is good, and that comes straight from your BCS theories, right? They said stay away from oxygen, because oxygen wants to absorb electrons. Then they said stay away from magnetism, because magnetism, they know from BCS theory, if you apply a magnetic field, it kills your superconducting state. then they said stay away from insulators, because basically the same argument as the density of states. If you don't have density of states at the Fermi level, you're not going to get a superconducting state. And then the last one, which is an addendum somewhere in the article, is stay away from theorists, because they don't know what they're doing. And so it's really great because I mean, I hope some of you have seen this comparison, because it's a nice comparison, that all of the high TCs basically violate a number of those rules, and that they contain oxygen, that the parent compounds are insulators, and that they definitely have some sort of magnetic phase nearby. Okay?
Also, some of them have quite low, sometimes have a low density of reactions, at least relevant.
Yeah, and there are other actual conventional superconductors that also have low density of states, but happen to have huge interaction attractive potentials. Yeah. And so overall, these rules are not very good. Okay?
Except the theorist rule.
Except the theorist rule. Stay away from theorists. So there's actually a long history of theorists claiming that their theories could be used to make a better superconductor. And the empirical observation is that this uniformly never works. Okay? However, I've had to adjust this. So I've used this slide for a number of years. I've had to adjust this because there actually is one explicit statement, which is not here, which has in fact been proved to explicitly work. And so within a BCS theory, without deriving BCS theory, does anyone remember what are the key elements? I mean, you seem to know BCS theory. What are the key things that give you a high transition temperature?
Fluctuations.
Well, what are the key things in your gap formula? You have a density of states. You have a potential. What is the other thing that's a primary scale in a BCS theory where you have phonons? The maximal phonon energy, the Debye frequency. So what's not here is, what if you could just make a material that has a huge Debye frequency, that has phonon modes at really high energies? Okay? So it's not on here, but someone years and years and years ago said, well, logically, if we can create a phonon-mediated superconductor and just drive it to have a huge phonon frequency, then that'll be an optimal superconductor. So in order to get a high frequency, you need, what is it, the most particles, the shortest distance between. So you want to find the smallest, lightest ions you can possibly find. And so it turns out, and there's a number of papers that have come out since 2015 on, what is this, hydrogen-3 sulfide, hydrogen sulfide. But it's H3S. And it's under extremely high pressure, OK? So these are some pictures. They take two diamonds, and then they wrap around, they put through it a metal contact, and then they pump hydrogen and sulfur gas into it, and then they compress it under pressure, and they basically clamp it with metal. And under some high pressure, which I don't particularly mind what it is, the gas crystallizes. And inside that little space, they now have formed a crystal that they have leads attached to. And then they can do experiments. They can do optical experiments on it. They can measure its conductivity, because they actually have like metallic leads that go in there. And they basically found that they could have superconductivity in this thing at 203 degrees Kelvin. Okay? 203. So that's what? Minus 70 degrees Celsius. So when I first saw this, I thought, well, that's stupid. Like, what are you going to do with that? And it turns out I've actually got to hold one of these things. It's about this big, and it's completely stable. It's just in a little metal casing, and you can just cool it down, do the experiment, warm it up. It's a completely stable, isolated superconductor that'll operate at an extremely high temperature. It's one of the coolest things I've ever seen. Okay? And this was not predicted, but after the fact, after it was actually found, it's a conventional superconductor. They can actually do density functional theory calculations and work out alpha squared F functions, just like Demler was talking about first couple of days. Once they work out those alpha squared F functions, they can do Ellie-Ashberg theory. And they get like 202 degrees or something like that. And they get the right answer. Okay? Yeah.
Excuse me, I thought it was first predicted. It was this Chinese paper in scientific reports or something like this.
Yeah, could be. I think it's been a target for quite some time. Now, super secret that I've only seen on a piece of paper on someone's desk, unpublished, was this number, 260 degrees, by someone who does Eliashberg calculations on another one of these things, but hydrogen 10 titanium. Okay? So keep an eye out. I don't know if you're interested. I don't know if you do density functional theory calculations. I don't know if you do Eliashberg calculations. Not that you're going to beat these guys to doing it. That's already done, I'm pretty sure, because they have the number. But there's now, as far as I'm aware, a prediction that if you could do the same thing, you have to put it in a diamond anvil cell, that this particular material will actually have a 260-degree transition. Okay? And that would be really cool. You, like, not your freezer, but at home, but like a
CO2 basically.
Yeah, you could basically cool it down really, really easily. And this would open all kinds of doors to really interesting, wild stuff. Okay? Just the idea that you have this little isolated superconductor, and who knows how that can be used in, I don't know, quantum computing or other computing devices or whatever. Obviously, this is not something you're going to use to transmit power. But what blew me away was how stable it was. How it was a object with leads that inside there is a superconductor operating at high temperature. So really cool developments. And this stuff is super unpublished, but hopefully we're going to have something really cool. So this was an extra slide I had to add in, because I wanted to go from these rules, and I wanted to tell you my picture on how it is that we create a better superconductor. So you want a recipe, right? Like you want to develop what is your recipe for finding a good superconductor. And this, like I said, never works, except in conventional superconductors. So if we want to study model systems, we can't, I don't know, we don't have simple rules that tell us what parameters to change to improve our superconductivity. So I want to ask a slightly different question. How can we, OK, so I don't like vague questions. I don't like things that are too big. Things that are like, how to make a better superconductor is too big. But you can actually have well-posed, not nonsense questions, which are, how can we find the parameters of a model that optimize the superconducting transition temperature? So that's a well-posed thing. No matter what model you look at, you could ask that question and try and find the optimal parameters for superconductivity. So this is what I want to show you for the next couple minutes. So in order to do that, we go back to our susceptibilities. And I'm thinking of susceptibilities, again, now in terms of linear response theory. So you've probably seen linear response. It's the truncation of the response of a density to the application of a field at the lowest order in the field. So you can go pull up your, we always use the Griffiths textbooks in our undergraduate courses. Do any of you guys use them, Griffiths? Is it international or not? I don't know. Not in Russia, I suppose. But you can look up your polarization density. And your polarization density looks like a susceptibility times the field within linear response. The point I want to make is that we are free to define susceptibilities to arbitrary fields. Okay? So we can define a susceptibility to be some derivative of any density with respect to any field in the limit of that field goes to 0. And that's your definition of a linear response susceptibility. Okay? So what we want to know is, what is the impact on the density of Cooper pairs to an infinitesimal superconducting field? I do have that little picture there. The bonus question was supposed to be, name a device which produces a superconducting field. Can someone tell me what is a device that produces a superconducting field? So I've got my little Fallout dude, Fallout boy, shooting a superconducting ray gun. What is a device that produces a superconducting field? What is a device that produces a magnetic field? What is a device that produces a superconducting field? A superconductor. Just a superconductor. And this is well known, OK? This is something called, for example, something called a proximity effect, where you take a material that's not a superconductor, and you jam a superconductor on top of it. And inside the normal material, you'll actually get superconducting Cooper pairs flowing. OK? So by applying a field, you can actually generate a phase. Now, for that phase to exist, on its own, you still need a susceptibility to that phase when the field is 0, so when there's no applied field. Okay? So in general, we take an anomalous spectral function. And this is, I did not do many-body theory of BCS equations, but the whole point in a BCS theory is you have both a regular Green's function and an anomalous Green's function. And the anomalous part of the Green's function looks like the creation of a pair that has momentum k and minus k spin up and spin down. Okay? But otherwise, it looks very similar to a Green's function. It is the off-diagonal elements of a Green's function matrix. So this is the object that we want to take a derivative of with respect to a superconducting field. Okay? And it happens that we can work out the math, and we can find that this actually directly relates to a very specific summation over very specific indexes of one of the basis representations of one of those susceptibilities. In the particle-particle basis, the susceptibility for the Q equals 0 and bosonic 0 frequency is directly relatable within some integrals. It's proportional to that susceptibility. Okay? So I now have an object in a specific basis that when I sum over it, it gives me how susceptible my system is to superconducting order. Okay? This has a special name in the literature. It's usually not written in this big, ugly notation we learned later. And it has attached to it a couple of extra prefactors that know about the symmetry of the superconducting order, whether or not it should be S wave or D wave or P wave, et cetera. So we can do some sort of calculation, and then we can enforce that symmetry. And we can ask, for which symmetry does our system become have a susceptibility? So here, for the D wave case, we see a very large susceptibility, which is off the charts here, for x squared minus y squared susceptibility. And these are calculations within the 2D Hubbard model for some parameters, which we won't worry about. If we had looked at S wave, we would find it was very negative, saying it was not at all susceptible to S wave superconductivity. But we can actually find regions where dxy is preferred. There's some very subtle regions where P wave superconductivity might emerge in very highly, highly doped systems. Okay? So this is a tool that we have at our disposal. And again, all of this comes from the fact that there's an eigenvalue that we can plot, and we can find where it goes through 1 or where it goes through -1. And that causes a divergence in a susceptibility. Okay? So the system, because superconductivity is a second-order phase transition, it should show a divergent susceptibility to superconducting fluctuations as you go through that transition. So that means that specific element of that susceptibility should diverge. And when we plot it as a function of t, when we plot the inverse, we see that it starts to fall off. And it's actually really challenging numerically to get this thing to go to 0 on finite systems. Okay? And that's why this eigenvalue representation is a little bit more powerful. Because if we can find one eigenvalue that diverges, that tells us that the whole system should be divergent. So we can do the most mundane thing. We can brute force solve the problem and look for superconducting states. So we look for those divergences in susceptibility, and or we could look directly for the order parameter, okay? The anomalous Green's function. When that thing's non-zero, it says we have a superconducting gap. We can perform those brute force calculations, and within the 2D Hubbard model for some particular parameters, we would find a dome that looks like this, and it has a dip down in the middle. This is a dome centered at the insulating point. Okay? So ideally, what we would want is some set of parameters where we have separate domes on the on the electron dope side and on the hole dope side. But for these particular parameters, it happens that those two domes touch each other qualitatively. Okay? Now, the calculation cost of doing this is absolutely astronomical. Okay? TC might be arbitrarily small. So if you don't know that there should be superconductivity in your model, doing this is really bad. Because you might never find it, right? Okay? So we had this idea of presenting, how can we find the parameters of a model quickly to optimize the superconducting transition temperature? And if the goal is to find a divergence, what we hope is, and you're not guaranteed, that at least with temperature and with a lot of other parameters is that you have sort of monotonic behavior of the susceptibility. And so for a sufficiently small change in model parameters, we ask, does the susceptibility increase or decrease? And you're basically stuck with the idea that it might be the case that before the susceptibility diverges, it just becomes large, right? So you can actually sit at some very high temperature and sweep parameter space where your calculation is easy and look for the region where the susceptibility is largest. And then you can cool your system. Okay? So we sweep through parameter space, and we plot our susceptibility to superconducting correlations as a function of doping and as a function of interaction strength. And we actually find that there is some complicated contour where right here is the highest, is the most susceptible to superconductivity. Right? Some people sometimes, you will see plots that look like this. These are called superconducting bananas, okay? Because they form this little banana shape, right? Great. So this lets us sort of play a game where we can look at the structure of the transition temperature. So on the left is the brute force transition temperature, and on the right is just the susceptibility at different choices of beta. So at some very high temperature, it's actually pretty unstructured, okay? But as you decrease the temperature slightly, you start to see the emergence of those peaked structures. And as you continue down, of course, at some point, you're actually going to go through the transition. And with factors of maybe 2 or 3 above the transition temperature, you can basically see that you have a large susceptibility to a certain type of ordering, okay? So this idea that you could take any model, do the same sort of procedure, and quickly sweep parameter space to look for superconducting orders, we think that maybe that could help with trying to identify places where there are going to be phase transitions. Okay? And this is really cool, because I like this statement right here. The normal state, all of this stuff at high temperature, these are susceptibilities in the normal state. These are susceptibilities in the normal state to superconducting fluctuations. The normal state material knows whether or not it wants to superconduct. And I think that's kind of a neat idea. And this lets us gain some insight into those parameters. But there's a caveat. It doesn't guarantee that there will ever be a transition. It could plateau. You could also have some other susceptibility diverge first, and then the physics has totally changed. Okay? So there's lots of situations where this would not hold. OK. So I'm going to just summarize everything that I've talked about in this entire second part. I talked a lot about the creation of numerical benchmarks in the 2D Hubbard model. I talked about extended Hubbard models. And the mentality that we have, and the reason why people study the two-dimensional Hubbard model so much, is just to use it as a foundation for testing new experimental or theoretical tools. Experimental tools in the context of cold atoms experiments, not so much in terms of material physics. But the ability to test and drive that development with a specific goal in mind. Okay? And then once we've established rigorously the full phase diagrams of that model, moving beyond that to harder problems. Finally, I showed you a couple of examples where I used a couple of things, one called fluctuation diagnostics, and the second, searching for superconducting fluctuations, and how all of this stuff was associated with 2-particle vertex functions and 2-particle susceptibilities. So with that, I'm done. So thanks for your attention, guys.
So do we have any final questions?
Everybody is full.
OK.
Yeah.
Well, I would have one. You spoke all about symmetries, and people have always told me that spontaneous symmetry breaking can only happen for continuous symmetries. And now you're looking at this Hubbard model, and you find, as far as I can understand, a broken symmetry in the sense that maybe one sublattice of a bipartition is almost empty, and one has a double occupancy.
So that I agree. I don't actually understand that. So I think the thing you're talking about is the charge ordering problem. Yes. Right. So I am fairly OK with the idea from a quantum mechanical perspective that when you put a non-local interaction, okay, I'm okay with this picture. Because I'm okay with the idea that we now have two energy scales that are going to interplay with each other, and that it's going to somehow become favorable for the system to violate its lattice symmetry. So this is the problem that you're having, is that you have this lattice symmetry, and you no longer have translational invariance, right? So for me, I'm okay here to have this happen when I have a direct interplay between two interaction scales, okay? I, however, 100% agree with you in the case of what's been published in Science, where did I put it? There's a Science article here where they get complicated stripe structures, okay, out of only the local U interaction. Because I can't even imagine how you can have a spontaneous breaking when you don't have the non-local interaction. So for me, I don't understand this problem where they get that even without that interaction, okay? So I agree that I don't feel that the spontaneous symmetry breaking should be allowed to exist, but I think that the V essentially imbalances your system and it causes it to happen, okay? It actually forces it. So it's like applying a magnetic B field or something like this to a system that means you don't actually have spontaneous symmetry breaking, okay? It's also possible, I don't know this for sure, that most of what's being seen in these small systems is highly system size dependent, okay? Because you will always have that symmetry broken in a finite system, okay? It's only in the infinite system where this really holds, where it's a truly spontaneous process. Okay?
Maybe I will comment, and maybe James will comment on this again. Basically, if you are hardcore theoretician, yeah, and if you look to what is called the phase diagram of Hubbard model, you just throw it away. Because it violates Wagner theorem. Yes, you have 2D system. Yeah, no antiferromagnetism there. It's destroyed by fluctuations at any temperature. No superconducting phase. It's PKT phase. Yeah.
Oh, yeah.
So that, if you want to treat this phase diagram somehow, you should incorporate the interlayer exchange or whatever.
Yeah.
Yeah. So
so this is an important point, because the stuff I'm showing at the end is very small system two-dimensional problems, okay? And I'm showing you a superconducting transition temperature, okay, in a two-dimensional model. A superconducting transition is a second-order phase transition, which is explicitly not allowed through Riemann-Wagner theorem. Unlike the metal insulator transition, which is first order, and that's okay. But you're not allowed to have the continuous transition. So this is truly an artifact of the fact that it's a small system size, okay? This is both problematic and helpful to theory on the justification that you want to use this as some window to understand the physics of cuprates, which are not actually two-dimensional materials. They are layered two-dimensional materials. And so people at least justify doing this stuff on the grounds that it contains some physics that the layered coupled layers, coupled 2D planes, would also contain. Okay? So the ultimate goal would be to break your two-dimensionality and alleviate all of these problems.